Of polystyrene sodium ion pairs in a 1 molar styrene solution in tetrahydrofuran for an ion pair concentration of 2.0 times 10 to the negative 3 molar. Calculate the relative contributions of contact and solvent separated ion pairs to the propagation process. Use appropriate data from table 512. Let's say KCS is the equilibrium constant for the interconversion between the two types of ion pairs. Namely, the contact and the solvent separated ion pair. So if this is the contact and this is the solvent separated ion pair, then the equilibrium constant is KCS. Now let Kc be the rate constant for the contact ion pair P minus C plus, and let Ks be the rate constant for the solvent separated ion pair So if X is the fraction of solvent separated ion pair, then 1 minus X would be the fraction of contact ion pair. The rate of propagation would be the sum of the contributions from the contact ion pair and the solvent separated ion pair. So let's see, for the contact ion pair, the rate of propagation, the contribution to the rate of propagation would be Kc times the concentration of the contact ion pair times the monomer concentration. Similarly, for the solvent separation pair, it would be the rate constant for the solvent separation pair times the concentration of the solvent separated ion pair times the monomer concentration. So plugging in the values, contribution of contact ion pair, so contribution of solvent separated ion pair. Okay, so let's look at this part from table 5-12. Kc is equal to 24 liters per mole second. Concentration of contact ion pair is given to us as 2.0 times 10 to the negative 3 molar. Of monomer concentration, styrene is given as 1 molar. So we can calculate the contribution of contact ion pair as 24 liters per mole second times 2.0 times 10 to the negative 3 molar times 1 molar, 0.048. So this is the contribution of contact ion pair to the rate of propagation. Let's see the contribution from the solvent-separated ion pair. So that is Ks times the concentration of the solvent-separated ion pair times monomer concentration. So Ks from the table 5-12 is 5.5 times 10 to the 4 liters per mole second. Concentration of the solvent-separated ion pair can be found from KCS and the contact ion pair concentration, where KCS is the equilibrium constant here. KCS times the concentration of the contact ion pair can give us the concentration of solvent ion pair. So since the contact ion pair is in equilibrium with an equilibrium constant of KCS with the solvent-separated ion pair, the concentration of the solvent-separated ion pair is equal to KCS times the concentration of contact ion pair. KCS from the table is equal to 2.57 times 10 to the negative 3. This times concentration of the contact ion pair is 2.0 times 10 to the negative 3 molar. So that gives us 5.14 times 10 to the negative 6 molar for the concentration of the solvent-separated ion pair. So plugging this into the contribution for solvent-separated ion pair here, we can say that contribution from the solvent-separated ion pair is Ks, which is 5.5 times 10 to the power 4 liters per mole second times concentration of the solvent-separated ion pair, which is 5.14 times 10 to the minus 6 molar times the concentration of styrene, which is 1 molar. So that is going to be the contribution from the solvent-separated ion pair. and that gives us 0.283. So the total rate of propagation is the contribution from the contact ion pair and the solvent separated ion pair, which is 0.048 plus 0.283, 0.331 capital M per second. So this is the rate of propagation. We need to find out the relative contributions of contact and solvent separated ion pairs. So we can find the relative contributions as the total is 0.331. So contribution from a contact ion pair is 0.048 divided by 0.331, and contribution from solvent separated ion pair is 0.283 divided by 0.331. So let's see what that comes to. .145 and 0.855. So these are the contributions. Also, we said that if one of them is x, the other one should be 1 minus x, and we can verify that by seeing that 0.145 plus 0.855 is 1.